Hello and welcome to the second part of my presentation. Again, my name is Hampus Monifjord. I'm a PhD candidate from Lund University in Sweden, and this presentation is on the workshop of low-cost spectroscopy techniques for mosquito surveillance, which is hosted by University of Cape Coast in Ghana. This part will focus on a hyperspectral fluorescence LiDAR. Currently, there are two copies of the instrument. One is in Ghana and one is in Sweden. It's also a low-cost instrument, costing around 6,000 euros or 60,000 cedis. It is a so-called Scheimpflug LiDAR, so I will briefly go through how the Scheimpflug principle is. The Scheimpflug principle is a technique used in photography. Normally you have a plane of sharp focus which is perpendicular to the optical axis of your camera's lens and sensor. The depth of field can be extended by adjusting the aperture, but there is a trade-off going on. So if you have a large aperture, you can have a short exposure, which gives you great time resolution, but then you get a poor focal depth. On the other hand, if you have a small aperture on your camera, you get a great focal depth, but then you need a long exposure, so then you get poor timing. The Scheimpflug principle angles the sensor and the lens so that this plane of sharp focus is tilted and it's instead along a plane that you want to image. In this case, it's tilted so that the railroad is imaged clearly. In this way, you get the benefit of both great timing and great focal depths. In our case, we will not use it on a railroad. We will rather image a laser beam, as you will see shortly. This is the Scheimpflug configuration illustrated for our LiDAR. A laser beam is emitted and subsequently imaged onto a tilted slit. The different ranges along the laser beam then corresponds to different positions along this slit. But since we don't only want the range information in this LiDAR, but also the spectrum, we have a grating-based spectrometric system placed after the tilted slit and before the camera sensor. This way, one dimension of the camera sensor records the range along the laser beam, and the other dimension of the camera sensor records the spectrum of the received light. The LiDAR looks like this. It emits a laser beam of 405 nanometer light, and it's designed to image this beam from approximately 6 meters to 150 meters. The LiDAR was first designed in CAD software, inserting mounts from Tor Labs, lenses from Edmund Optics, and custom-made parts to be 3D printed. The design was validated and adjusted with ray tracing through CMAX, and then all components were bought and 3D printed, respectively, before being assembled, as seen to the right. Since the LiDAR acquires both range and wavelength information, the data file is three-dimensional, containing light from approximately 400 to 820 nanometers. This includes the elastic laser light and any fluorescent signal. This could, for example, come from differently colored fluorescent powders, as marked on the wavelength axis in this figure. In order to remove all the background signal, the laser is multiplexed, and every other exposure is with the laser on and off. Hence, the background can easily be removed with interpolation. The spectral resolution is around 6 nanometers, time resolution around 8 milliseconds, and the range resolution varies from around 2 centimeters to 80 centimeters, depending on the range. Since insects are not particularly fluorescent, this LiDAR is used with fluorescent tagging techniques. We have done this for bees in a commercial beehive, where the bees have to crawl through a fluorescent powder as they exit their hive, as seen in this image. Then we monitor the insects that fly through the LiDAR, and we see if they only have an elastic echo or if they have both elastic and a red fluorescent echo. This way we can deduce if they are our tagged bees or any other insect. This can be extended to more hives being tagged with different colors. Then comes the question, can we do this with mosquitoes? They don't have hives that we can attach a powder tray to. We have found that feeding mosquitoes with fluorescent sugar water can function as a fluorescent tagging method. In this case, we left mosquitoes to feed from a green fluorescent sugar water for some hours. Then we picked one with a tweezer and we held it into the LiDAR at around 10 meters range, which produced a strong LiDAR signal. This indicates that this method works. Last year at University of Cape Coast, we tried to replicate and expand on this mosquito tagging method. Here we marked 4 different mosquito species with different fluorescent tags. We let them feed on the sugar water and then we released them into a flying chamber, positioning the LiDAR to measure into this chamber. The result was, however, unsatisfactory. The mosquitoes were not keen on flying in the chamber, so we recorded no mosquito observations, neither elastic, which would indicate a non-successful tagging, or any fluorescent observations, which would indicate a successful tagging. I believe, however, that these experiments could be tried again with more focus on how to get the tagged mosquitoes to fly in through the LiDAR beam. This concludes my presentation, and thank you for inviting me to present at this conference. And I would again be very happy to answer any of your questions.